Okay, so am I audible, right? Okay, so hope am I audible, right? So let me share my screen first. Okay, so so I am Subrata Samanta and one of the TF for the thermal physics course that is taken by Professor Demal Banerjee in this semester at NPTEL. So today I will discuss assignment 11 problems, okay, and solve these problems. So this is basically previous year assignment 11 problems. So hope at the end you will able to solve this year assignment 11 problems. It's very similar, okay. And if you have any questions, any doubts, okay, you can directly ask, okay, during the class, okay. Okay, so let me share my screen first. Okay, hope my screen is visible now, right? Okay, so this is assignment 11, okay, previous year assignment 11 problems, okay. So I will solve one by one. So so far any questions, I mean any questions from the week content or previous week assignments, okay, any doubts related. So if you have any questions, you can raise your questions here, right? Don't hesitate to ask any questions, okay. Okay, so it seems that there is no question, so I'll solve the questions assignment week problems one by one. So the first question is that so calculate the change of melting point, okay, naphthalene per atmospheric change of pressure, right? So atmospheric pressure, that means P is 1 atm, right? Given the melting point is 80 degrees centigrade, so T is temperature is 80 degrees centigrade, so it's 273 plus 80 Kelvin, right? Okay, and the density of solid is given, so latent heat is also given, so latent heat is L is 35.5 calorie per gram, right? And the density of solid, so rho s solid, this is 1.145 gram per cc, right? And density of liquid, rho l liquid, so is 0.981, right? So 981 gram per cc, right? So this data are given, okay. So you have to calculate the change of melting point, okay. Okay, so how to calculate this? So let's first copy the data, okay. So how to calculate this? So okay, so this is the problem number 1. So these data are given, right? Latent heat, pressures and temperatures, right? So you know the Clausius-Clapeyron equations, right? So the Clausius, so we use the Clausius-Clapeyron equation. So use Clausius, right? Clapeyron equations, right? So use Clausius-Clapeyron equation. So this is basically where the working medium, so in this equations is usable when the working medium, so when the working medium okay, is the interface of two phase, and that is basically first order phase transitions. Okay, so is the interface of two phases, and it's applicable for the first order phase transitions, right? So the Clausius-Clapeyron equations. So in this case, so this is basically so in the problem, so we use this Clausius-Clapeyron equations, okay, to calculate the melting points. Okay, so this is basically the equations is dt over dp, right? Or we can write dp over dt, the change in pressure over change in temperatures, okay, over the temperatures. Okay, so dp over dt is L over latent heat over T, the temperature, times V2 minus V1, right? So this V2 V1 basically volume, right? And the specific volume, so 1 gram moles. Okay, so this is basically 1 over density, right? So V2, I think, let's say for in this case liquid to solid, so I write VL minus Vs, right? So where the VL is basically 1 over rho L, and Vs is specific density, so it's 1 over rho S. Okay, so 1 over specific volume, 1 over specific density, right? So this is the density, okay, and 1 gram mole, so small Vs, okay, 1 over rho L and 1 over rho S, right? So now we have to calculate dt. So this is dt, the dt equals to, from these equations, okay, so this is our T times 1 over rho L minus 1 over rho S, right, divided by L, right? So latent heat times dp, the change in pressure, right? And that is basically your 1 atm. So now if you go back to the problems, okay, problem statement, so yeah, so problem statement is calculate the changing melting point naphthalene per atmospheric change of pressure, right? So 1 atm, the delta p, so p is basically delta p, right? Okay, so your delta p is 1 atm. So the change in pressure, okay, so change of pressure 1 atm, okay, so delta p 1 atms more specifically, so this one is delta p 1 atms. So now if we use this, so your this is basically now to calculate delta t, okay, the delta p, okay, when the delta p 1 atm, right? So all the data are given, right? So your temperature T is basically 273 plus 80 Kelvin. Now we use SI unit, CGS unit, right? So all are in the CGS unit. Okay, the latent heat is calorie per gram, right? And this is gram per cc, and this is also gram per cc. It's CGS units. Okay, so we use CGS unit, right? Now what is delta P in CGS unit? So delta P is 1 atm. Okay, so this calorie per gram, we have to convert this in the CGS unit, right? So 1 atm is equals to, so first the delta P 1 atm, right? So this is basically, so in CGS unit, right? So it's basically 1.013, right, into 10 to the power 6. So what is the CGS unit then? It's basically dyne over centimeter square, right? So please check that. Okay, so this is your one of the homework. Okay, so 1 atm is equals to, so the 1 atm equals to 1.013 times 10 to the power 6 dyne over centimeter square. So first convert it to Pascal, right? So you know that the 1 Pascal is 1 Newton per meter square, right? Now we just convert 1 Newton to 1 dyne, okay, and meter square to centimeter square. So this is a very simple steps. Okay, okay, and at the end we will get that you will get that 1.013, okay, times 10 to the power 6, okay, dyne per centimeter square. Now the what is the latent heat L? So L is 35.5 calorie per gram, right? So gram is fine, but the calorie, so we have to convert calorie to CGS unit. So what is the CGS unit? Is arc, right? So first convert calorie to joule. So first convert, so basically you have to convert calorie. So you have to convert first calorie. So 1 calorie equals to 4.2 joule, and 1 joule equals to 10 to the power 7 arc, right? Okay, so it's clear. So therefore your latent heat L, so now I write explicitly that, so 1 over rho L, so 1 over so rho L basically 0.981, so 1 over 0.981 minus 1 over 1.141, right? So 1.141 145, sorry, so 1.145, right? So your delta T equals to this over L, so L with 35.5, so 35.5 calorie per gram. So first I convert to uh, joule per gram and then arc per gram, right? So it's 4.2 times 10 to the power 7 arc per gram. Now what is the delta P? It's this one, right? So this is your delta P. So delta P is 1.013 times 10 to the power 6, right? So now everything is the CGS unit. Okay, it's perfectly fine, right? So you calculate this. Okay, use your calculators to calculate this. Okay, so then you find that 0.035 Kelvin. Okay. So please cross check the answers. Okay, so 0.035 Kelvin. Okay. So this is your change in the melting point temperature delta T, right? Okay, any question? Okay, so let's match with the answers. Okay, so 0.035 Kelvin. So let's check the options. Yeah, so the option C is correct, right? So this one is correct. Okay, so option C. Yeah, any question? So this is very straightforward. First we calculate okay, so all the data is given, so use Clausius Clapeyron equations, okay, to calculate the delta T, the change in melting point temperatures, okay, where the changing pressure is given, what ATMs, okay, and the VL is the volume, so it and the density is given, so convert density to volumes, okay, and consistence with the units. Okay, so if you use CGS units, okay, so constantly throughout you use CGS unit, okay, change everything in the CGS units, or if you use SI units, okay, then you accordingly changes every quantities, okay, in the SI units, okay, and ultimately the result is the same, okay, so that does not change. Okay, so whatever your system, I mean the units are, okay. Okay, so this delta T is that 0.035 kelvins. Okay, okay, so it seems there is no more questions, so then I will move to the second one. Okay, so in the second problem, so the sublimation curve of solid NH3, right, is given by LNP. This is basically an equations. Okay, so I wrote it down that LNP equals to 23 minus 3750 over T, and the vaporization curve at so this one is the sublimation curve. Okay, okay, and the second one is the vaporization, right? So vaporization curve, right? So this is basically LNP is 23, sorry, 19.5 minus 3050. So 19.5 minus 3050 over t, right? So these two data are given, right? And where the p is basically the millimeter of Hg, right? So another equations, and where the p is basically millimeter of Hg and t is in Kelvin. Okay, calculate that triple point temperatures. Okay, the temperature at triple point of NH3. Okay, so there is a 2 points, two phase basically. One is the sublimations and is the vaporizations, right? And you have to calculate the triple points. Okay. So now what is the triple point? Okay, so if you know what is the triple points, then it's very easy to solve these problems. Okay, or you can quickly answer the questions. Okay, so calculate the temperatures at the triple points. Okay, this is your task. So this is your task. So your problem number 2. Okay, so these two data is given, right? So at the triple points, right, now the point is that, so at the triple point, okay, so the sublimation curve and the vaporization curve must meet, right? Because the common point is the triple points, right? So at the triple point, so at the triple point, both sublimation curve, both sublimation and vaporization curve, so vaporization curve, okay, must meet. Okay, that will intersect. Okay, so must so must meet. Okay, so that will be basically the intersection point. Okay, so the triple points is basically the intersection point of so basically the intersection point of so intersection point of two curves. Okay, two curve. Okay, so now we know what is the equations of the two curve, right? So sublimation curve, this is the equation, this is basically equation number 1, and your vaporization curve, okay, at equation number 2, right? Okay, in the plane, okay, in the PT plane. So now if the two curves are met, okay, at the common point, at the intersection point, okay, so the values of PT is the same for the both the cases, for both equations 1 and both equations 2, right? At a common point T, where they where these two curves are intersect, right? So that means we can write, so at intersection point, so at intersection point, we can write, basically we equate two equations. Okay, so lnp, I substitute lnp, right? So this is basically 23 minus 3750 over t is equals to 19.5 minus 3050 over t, right? So this point is clear or not? Okay. So I substitute lnp, okay, from equations 1 and 2, okay, because they are intersect, right? Okay, and the intersection point we can write this. Okay, so this point is clear or not? Okay, any questions from this point? Okay, so no question, right? So this point is perfect. So the next task is basically you have to calculate the temperature, right? So it is easy. So you just think that your 3750 minus 3050 over T is equals to 23 minus 19.5. So your T equals to basically 700 over, right? So it is basically 3.5, right? So you just multiply it with a 10 both sides, so you are 7000 over 35, so it's 200 Kelvin, right? Okay, so this is 200 Kelvin, right? So let's check the option. So it's 200 Kelvin. So this is your temperature, so at common point. Okay, so let's check the option. Yeah, so the temperature at triple point, so this is basically common point, so this is basically at 200 Kelvin, right? So option A is correct. Yeah, any question, right? So once you equate this, then it's basically algebraically straightforward. Okay, we just manipulate this equations. Okay, so I'll move to the next one. This is the problem number 3. Okay, yeah, any question? Okay, so in the problem number 3, it's basically the melting point of ice changes by this amount. Okay, so this is your, let's say, delta T, okay, or T, right, for a change in pressure by 1 atm. So your melting point of ice changes delta T, it's 0.0072 degrees centigrade when the delta P is 1 atm. The saturated vapor pressure of water at 0 degree centigrade and 1 degree centigrade is 4.6 millimeter of Hg, okay, and 4.94 millimeter of Hg respectively, right? Find the temperature of the triple point. Okay. So again in this problem you have to compute the temperature of the triple point, right? Okay, when the melting point of ice changes by this amount and the pressure it changes at on atm, right? So at the triple points, okay, so then how to solve this problem? You have to calculate the temperature at the triple point. Now that the triple point, so the saturated vapor pressure at triple point, so saturated vapor pressure at triple point T degree centigrade, okay, it's given by P equals to 4.6. Okay, so here this is only very crucial. So 4.6 is the yeah, so it's the 4.6 millimeter of H, right? So at 0 degree centigrade, okay, and then at 1 degree centigrade is 4.94, right? So 4.6 and 4.94, right? So 4.6 at 0 degree centigrade plus the change in basically 4.94 minus 4.6 times your T, right? Since the triple point temperature is a T degree centigrade, okay, so times T, so this is basically the pressure is basically then 4.6 plus 0.34 times T is the millimeter of Hg, right? So this is millimeter of Hg, right? or in short millimeters. So this is the saturated vapor pressure at triple point, right? So decrease in pressure at triple point due to change in temperatures. So let's say decrease. So the next, so this is your step 1, right? So let's say A and this one is the B. Yeah, so in step A there is any questions? Okay. Okay, you have any questions you would raise, okay, in the meantime. So in case of step B, so this is basically decrease in pressure at triple point due to change in temperature, due to, let's say, change in temperature from 0 degree centigrade to T degree centigrade. Okay. What is the decrease in pressure P? So this is the upper one is the saturated vapor pressure, and this is basically decrease in pressure, right? So then P equals to, again the same thing, 760. Okay, this is basically 76 centimeter centimeter of Hg, that means 76 millimeter of Hg. Okay, minus 0 degree centigrade is 1 atm. Okay, so 76 centimeter of Hg. So I converted to millimeter, and then minus your 4.6 plus 0.34, right? So this is basically the difference between 0 to 1 degree centigrade. This times T, right? So this one, right? And then everything is the millimeter of H, right? So first you calculate this. So now this is basically your P prime, okay, or delta P. Okay. So 76 1 atm minus this, okay, minus this, okay. Right. Okay, so hence the melting point, so delta T equals to, so this is basically melting point change, right? So it's 0.072. So this is basically okay, so this one is delta P. Now if you use the Clausius-Clapeyron equations, okay, so your delta P over delta T, right? So this is basically delta P prime is decrease in pressure, okay, and this is delta P is the change in the pressures, okay. Okay, so this is basically why the delta P is 1 atm, right? So delta P is 1 atm. It's basically 760, okay, millimeter of Hg, right? And this one is basically, yeah, so this one is basically your 760 minus this, so 760 minus 4.6 plus 0.34 T, okay, over T, right? So this is basically the temperature at the triple point. So at the triple point, so this is basically the T is the temperature, okay. So where T is the temperature, so temperature at the triple point, okay, triple point, right? So we have to solve this, right? So delta P is 1 atm, so that means, and delta T is given, so delta P is given in the problem. So this is basically okay. So what is the delta P? Yeah, so delta P is this. So I copy this to data. So that is given in the problem, right? So yes, so delta T is 0.072 and delta P is 1 atm. So if we plug this into these equations, so we get that yeah, so 760. So 1 atm means that 760 millimeter of Hg. So I convert this, so 760 over 0.0072. Okay, so I use degree centigrade. So which is equals to 760 minus 4.6 plus 0.34 times T, okay, over T, right? So now this is basically T equals to, so this is the temperature at a triple points, okay. So T equals to your 760, sorry, 0.0072 my times 755.4 minus 0.34 times T, okay, over 760, right? So over 760. So this is basically, and it's degree centigrade because I use 0.0072 is the degree centigrade, sorry, and these are the dimensionless, okay, other quantities, sorry. So it's basically ratio of the same quantity, sorry. So okay, so it becomes 0.00756 degree centigrade, sorry. So please cross check this number, okay, just calculate this, use your calculator and calculate this. So I first one, so there is also T, right? So in both sides, so this and this, okay. First you uh, uh, yeah, first you put in the left hand side and then have to calculate the T, okay. So this is basically T equals to this, okay. Okay, so any question? Okay, so let us check the options, okay. So 0.07156, this is problem number 3. 0.07156, yeah, so option A is correct, right? Okay, yeah, any question? So first calculate the saturated vapor pressures at the triple points, okay, and then you calculate the change in pressure, okay, okay, at the triple points, okay, when the temperature is changes from 0 degree centigrade to T degree centigrade, right? At 0 degree centigrade, you know the pressure is basically your on atm pressure, right? That is given, okay, change in pressures, right? But if you calculate the delta P prime, the change in pressures or the decrease in pressures, right, at the triple points, okay, when the temperature changes at 0 degree centigrade to T degree centigrade, and T degree centigrade is the temperature at the triple point, okay. So due to this change in temperature, you first calculate the delta P, right? Okay, at the delta P, the change in pressure, right, and that is basically decreased, okay. So okay, so it seems that there is no more questions, so then I will move to the fourth one, right? So yeah, fourth question. Okay, so in the fourth problem, so calculate the specific heat of saturated vapor from the following data, right? So you have to calculate the specific heat of saturated vapor, specific heat of saturated vapor, but the data is given the latent heat of Vaporization calorie per gram, boiling point of water 100 degrees centigrade, okay, and DLDT is given, and the specific heat of water is given, right, at 100 degrees centigrade is given, right. Okay, so first note down what is given, what are the given data. Okay, so the latent heat L of the vaporization is 539.3 calorie per gram, and the boiling point of water is T is basically 100 degrees centigrade. That means it's 273 plus 100 is 373 Kelvin, and DL over dt is 0.64 calorie per gram Kelvin, and the specific heat of water, so the specific heat of water basically let's see liquid, okay, water Cl, okay, that is given 1.01 calorie per gram Kelvin, right. So 1.01 calorie per gram Kelvin, okay. So you have to calculate from this data, you have to calculate the specific heat of solid, right. The specific heat of liquid is given, so this Cl, the specific heat of liquid or water, specific heat of water at 100 degrees centigrade, okay, is a boiling point, okay. And we have to calculate the specific heat of solid. So if you use the equations, the equation is basically dl over dt, right, minus L over T is equals to your specific heat of solid Cs minus Cl, right. So this Cs is the specific heat of solid, okay. So this Cs is the specific heat of solid, okay. Yes, so specific heat of sorry, saturated vapor, right, not solid, sorry, the saturated vapor, okay. So liquid to saturated vapor, so the specific heat of let's say a saturated vapor, okay. Specific heat of saturated vapor, right, you have to calculate this, okay. Sorry, so this is not a solid, okay. So Cs is the saturated vapor Cs, okay, and Cl is the specific heat of water, okay. So now the data is given, right. So your DLDT is minus 0.0 sorry 0.64, okay, which is equals to L over T, or like minus L over T, so 539.3, and your temperature T is 373 Kelvin, and this is basically Cs minus Cl is 1.01, right. So here I use calorie, so because your Cl is also given in calorie, okay, so no need to change, okay, so make it consistent, okay. So it's 1.01 calorie, because this one is also calorie, okay. So use calorie, okay, in everywhere, okay. So then you just calculate Cs from this, okay. So your Cs, the specific heat of saturated vapor, okay. So this is basically 1 minus 1.0758 calorie per gram, right. So calorie per gram Kelvin, right. So this one is the calorie per gram Kelvin, yeah. So this is calorie per gram Kelvin. Okay, so this is basically your the specific heat of saturated vapor. Okay, so please cross check the answers. Okay, so use your calculator, calculate this, okay, and check these answers. Okay. So minus 1.0758. Okay, so let's check the options. Okay, any question? Okay, I'll check the options later, but first if you have any questions, okay, so please feel free to ask. Okay, it seems no more questions. Okay, so then okay, so I'll check the options. Okay, so it's on minus 1.0758. Okay, this is your the specific heat of saturated vapor, right? So minus 1.0758. Yeah, so this is basically close to option D, right? So minus 1.08 calorie per gram Kelvin. Okay. So the option D is correct, right? Okay. Okay, so then I'll move to the next one. So it's problem number 5. So for a single component system, the specific heat at constant pressure during first order phase transitions. Okay, so how to calculate this? How to know that the change the specific heat at constant pressure Cp, okay, during the first order phase transitions. Okay, so for a single component system, so if you have a single component systems, okay, what is your Cp? Okay, okay, at the phase transitions point of critical point. Okay, so at the critical points the Cp basically diverges, right? So how do you know? Because the Gibbs free energy, okay, so your Cp, the change in sorry, the specific heat at constant pressure, okay, Cp is basically related to the double derivative of the potentials, right? Sorry, the first derivatives, and if you know the Gibbs free energy is the first order, the first derivative is the discontinuous, okay, so that means is the first order phase transitions, okay. And if you take on more derivatives, okay, it's basically diverged, okay. So this one is the infinity, right? So for the first order phase transitions, the Gibbs free energy, okay, is basically discontinuous, okay, the first derivative of the so first order phase transition is basically the first derivative of the Gibbs free energy is discontinuous, okay, the Gibbs free energy, okay, is discontinuous, okay. So discontinuous, new answer. So that's why it's the first order of instance, and the specific heat is basically related to that one more, so it's diverse, right? Okay, so it's infinity. Okay, so option C is correct, right? So which order of, so this is for a single component system. So if there is a multiple component, then there might be different. Okay, right? So I think it depends on other things. Okay? If it is a multi-component system. Okay, so I'm not going into this system now. Okay, so if time permits, I'll discuss later. Okay, yeah. Any questions? So okay, so then I'll move to the next one. So the next question is that which order of derivative of Gibbs free energy is discontinuous for a second order phase transitions, right? Okay, so this is just we discussed, right? So for the first order phase transition, the first derivatives of the Gibbs free energy is discontinuous. Okay? So for the second order phase transitions, so for second order phase transition, okay, so for the second order phase transitions, then the second derivative of the Gibbs free energy is discontinuous, right? So second derivative of the Gibbs free energy, right, is discontinuous, right? So that means the second one. So option B is correct, right? Right? Yeah. Any question? Okay. So then I'll move to the question number 7. Second, the Clausius-Clapeyron equations holds for. Okay, I already discussed, right? So the Clausius, so in the beginning I already discussed the Clausius-Clapeyron equations holds for only first order phase transition, right? So option A is correct. Okay. Any doubt? Okay. So the problem number 8, right? So in the 8, yeah. So for the L is given latent heat. So L is basically A plus BT plus CT square. Find the difference of specific heats, liquid and saturated vapor. Okay. So again we use the same equations. Okay. So which problems? Yeah. So in this problem we calculate the specific heat of saturated vapor, right? So it's problem number 4, right? So we use this. Okay. So again we use this to calculate this. So calculate the saturated vapor of to calculate the saturated vapor. Yeah, so the difference in of specific heats of liquid and saturated vapor. So Cl minus Cs, right? So this is basically your dl dt minus L over T, right? So now L is given. So dl dt, you first compute the dl dt from this. Okay. This is problem number 8. right? So first calculate dl dt. Okay, so what is the dl dt? So the dl dt, so on more derivatives, so b plus 2ct, right? If we derivative with respect to t, okay, and l over t is basically a over t plus b plus ct. So now the cl minus cs is basically b plus 2ct minus a over t plus b minus b minus ct, right? So b cancel, it's ct minus a over t. Okay, so this is a constant, so ct minus a over t, right? So let's check the options. Okay, this is very straightforward. Okay, so the l is given. Okay, so take on derivatives with respect to t, so we find dl over dt, right? And when you find dl over dt, we use these equations. Okay, l is already known, so l over t is basically just divided over t. Okay, right. And cl minus cs, it becomes this. Okay, this 2-3 line calculations. Okay, so we'll find this. Okay, so let's check the options. So cl minus cs is yes, so ct minus a over t, right? So option A is correct. Okay, yeah, any question? Okay, so no question, right? Okay, so then I will move to the next one. When ice melts, its volume decreases, right? So with increase of pressure, the melting point of ice. Okay, so I repeat the question. So when ice melts, its volume decrease. That's true, right? And so with increase of pressure, the melting point of ice obviously decreases, right? So option B is correct. So in the problem number 10, right? Okay, so far any question? Okay, so it's not, then I will move to the last one. So in the last problem, in a saturated solution of table salt NaCl is in equilibrium with a crystalline of NaCl and the number of independent intensive variable f, right? Okay, so to solve these equations, you have to know the Gibbs phase rule, right? So what is the Gibbs phase rule? Okay, so I will discuss in short. Okay, so what is the Gibbs phase rule? So it's problem number 10, right? So first I will discuss the Gibbs phase rule. So this is basically mixture of different substance, okay, and that is really multi-component systems. So consider a multi-component systems. Consider a multi-component system that is basically the mixture of different substance right. So it's basically chemically independent constitute of the system, sorry. So different substance means chemically independent, okay, constituents of the system. So constituents of the system, right. So in this multi-component system, so let's say containing C components, okay, and P different phases, so containing C components and P different phases, then the number of degree of freedom F of the systems, okay, then the number of degree of freedom of the system this is basically F, and that is your intensive variable. So this F is basically in the questions is the independent intensive variables, okay, that means the number of degree of freedoms, okay. So this is same F, okay, so same F, okay, number of independent intensive variables. So this F is basically also the number of independent intensive variables, intensive variables, right, and that's the number of degree of freedom of the system, right. So this is exactly same, okay. So F, that's is C minus P plus 2, okay, where the C is C components, okay, and P different phases, right. So this CP, right, so C components and this C and P different phases, and the number of things is F is basically C minus P plus 2, okay. So that is the yeah, so this is known as Gibbs phase rule, right. So this is basically so this is Gibbs phase rule. So Gibbs phase rule, okay. So now in the problem, okay, so now go back to the problem. So in the problem we have a NaCls, and that is basically saturated solutions of NaCls in equilibrium with a crystalline. So that means there is a two component, so two component, right, basically salt and water, okay, and there are two phases, right, it's basically solutions, solutions of NaCl and the crystalline, right? So solid crystal, so solid crystal, right? So two phases and two components. Okay, so then according to the Gibbs phase rule, your F, the number of independent intensive variables, the degree of freedoms, okay, is C minus P plus 2, right? So where C is two components, so C equals to 2, and two phases, P equals to 2, right? So this is basically 2 minus 2 plus 2, so it's 2, right? So that means your number of intensive variables, independent intensive variable is 2, right? So option C is correct. Right. So let's do some other examples. Okay, so let's first any questions, okay, from for this. So this isn't the last problem, sir. So in the saturated solutions of table salt, so this is just solutions of table salt, that is one phase, okay, and the crystalline of NaCl, the other one, okay. So there is two phases, and the two components is basically salt and water, right? Solutions of table salt, saturated solutions of table salt, that means there is some water and salt, okay. So these are two components, right? So it's clear, right? Okay, any question? Okay, so let's discuss something from this. Okay, so let's say for a single component system, so for a single component system, so that means C equals to 1, okay. So then your F is 3 minus P, right? Right. So first case, let's, if there is only one phase, okay. So if there is a one phase, right? So if there is a one phase, then your P equals to 1, so that means F equals to 2, right? So whole PT plane is accessible in this case, right? Because F equals to 2, so there is a 2 degree of freedoms, okay, and whole pressure temperature PT plane, right? So whole PT plane is accessible. So now the second point, if p equals to 2, let's say there is a 2 phase. So first I choose a single component system, that means c equals to 1. Now my from Gibbs space rule, the number of degree of freedom is 3 minus p, right? Basically c minus p plus 1 plus 2, right? So if c equals to 1, then is 3 minus p, right? So now if you choose, let's say there is only one phase, that means p equals to 1 and f equals to 2, so there is a 2 degree of freedom, then whole pt plane is accessible. Now if we choose p equals to 2, that means there is a 2 phase. Okay, so then f equals to 1, right? Because this is basically some line. Okay, so coexist line in the pt plane is accessible, right? So coexist okay, line in the pt plane, the pt plane is accessible, right? Okay, so now if you consider p equals to 3, if there is a 3 phase, so this implies that f equals to 0 is basically only one point where 3 phases coexist for a single component system. Okay, so only one point, okay, where 3 phases coexist. Okay, 3 phases, because any p equals to 3, right? So 3 phases coexist. Okay, so that is basically your triple point. So this point, so on point, so that is basically your triple point. Okay, when is a single component systems, okay, and there is a 3 phase. Okay, so for a single component systems, the 3 phase must coexist at a point, not over a line, not over a surface. Okay, so at a point, and this point is the triple point. Okay, it's clear. Okay, it's clear now. So if you have any questions, please ask us. Okay, okay, so if not, then I will discuss some other things. Let's say okay, so let me check things we'll discuss. Okay, so I think this one is good. Okay, so let's just discuss some other type of systems. Okay, so far we are dealing with only gaseous systems, right? I mean, but what is the case for if there is a some elastic rod? Okay, systems, basically the elastic rod. Okay, so okay, so let's for gaseous systems, we know that okay, so for gaseous systems, basically the first law of thermodynamics, first law of thermodynamics, okay, so is du is tds minus pdv, right? So this is basically dq over dw, right? So it's dq is inexact plus dw, right? And for other systems, so this is for gaseous system, right? So for other system, so for other systems is dw is basically x dx, okay? X, so capital X, small dx, okay? So where x is your generalized force, generalized force, okay, and your small x is the generalized displacement, right? Generalized displacement, right? So from this you can also classify the intensive variable and the extensive variable, right? So which one is the extensive variable for capital X, from capital X or small x? So small x, right? So small x is the extensive variable. So this is basically your v, okay, pdv, right? So let's start that pdv, right? So v is the extensive variable and p is the intensive variable, right? So this one is the extensive variable, and this, the capital X, is the intensive variable, right? So let's make a chart for a general things, okay? So x, capital X and small x, okay? And we have a system, let's say fluid, right? So for fluid case, what is your generalized force? Is rho, right? Is minus p, right? Fluid system, okay? And also pressure, right? And x is basically your v, right? And what is your dw? Yeah, so here I put a minus p because if we decrease the volume, okay, the pressure will be increased, okay? So that's why minus p, okay? So and dw is basically minus p dv. The sign is basically conventions, okay? So if we decrease the volume, then increase the pressure, okay, right? So the next system is the elastic rod, elastic rod, okay? So for elastic rods, then what is generalized force? Capital X is F, right? Is force, and this one is L. This is basically FDL, length, okay? So it's L is length and F is the force, right? So FDL, okay, tension, okay? And for dielectric medium, dielectric, right? So for dielectric medium, the electric field E and is the PE, right? Okay, it's the polarization, sorry. So this is basically your E times dPE, right? Is the dipole moment, okay? And for magnetic system is the magnetization, right? So electric polarization rho PE, okay? And in this case the magnetizations M and the B for magnetic system, right? So it's basically BDM, okay, right? So that is basically for a general systems, okay? Okay, so let's pass yeah, any question? Yeah, if you have any questions, please feel free to ask. Okay? Okay, so any question? Right? So basically for elastic case is the electric field and polarizations, okay, and for magnetic case is the magnetic field and the magnetizations, okay, BDM and PD, right? EP, EP, DP, right? For electric dielectric systems, right? So now if you focus on the elastic rod, right? So if you focus on the elastic rod, so elastic rod, okay, so consider a rod with cross section area, cross sectional area, let's say A. So consider a rod with cross sectional area A and length small l, right? So this is your area and this is your length, okay, or let's say capital L, okay. Define the linear expansivity, okay, of the constant tension, okay, at constant tension F. So if you define a linear expansivity, so define linear expansivity of the rod, so expansivity, okay, at constant tension, right? So at constant tension F, okay, so your alpha F is basically 1 over L delta L over delta T, right? That is a constant tension F, okay, which is greater than 0, okay. This is for metal wire, so it is for metal wire, okay. And for rubber, so it's greater than 0 for metal wire, right? So this greater than 0 for metal wire, okay, and alpha F is less than 0 for rubber, right? So this linear expansivity is negative, okay, for rubber, right? So for rubber, this alpha F negative for rubber, okay. So now what is the first law of thermodynamics in this case? The first law of thermodynamics in case of elastic rod, so first law of thermodynamics is basically du is TdS plus FdL, okay. And the Helmholtz free energy, so where U is the internal energy, right? So this U is the internal energy, right? So here U is the internal energy, okay, and the Helmholtz free energy, so Helmholtz free energy F is equals to U minus Ts. Okay. So here the dF is minus SDT plus FDL. Okay. So this is your dF, right? Where F is the tension, so the generalized force. Okay. So this F is basically your generalized force, that is the tension, right? Okay. Right. So therefore your S, the entropy, so your S is basically minus del F from the partial derivatives. Okay. So from partial derivatives, so this F is basically your minus del F over del T, right? Because this is a coefficient of dt. So minus del F del T, okay, at constant L, right? And your small f is the tension, is basically del F over del L at constant temperature, right? So now if you know that this dF is the exact differential, so okay, Helmholtz free energy, so this dF is the exact, sorry, I think it's the exact differential, exact differential. So that means del 2f over del T del L equals to del 2f over del L del T. Okay. So which implies that del S over delta L at constant temperature T is equals to minus del F over del T at constant L. Okay, so this is basically the Maxwell relations for elastic rods. Okay, so this is one of the Maxwell equations for elastic rod, right? So this is one of the Maxwell equations, the Maxwell relations. Sorry, Maxwell relations. Okay, so that is the right way to say. The Maxwell relation for elastic rod, right? Okay. Right. So why these Maxwell relations are important, right? So now the question is that why the Maxwell relations are important, right? So because the thing is that, so if you know this equation, right? So del S over del T, del S over del L equals to minus del F over del T, right? Okay. So but the experimentally very difficult to measure the change in entropy, right? Because it gives a very fundamental information about the system, right? So how the entropy changes over the length, it's a very fundamental concept, or if you put a very fundamental information, but you can, I mean, experimental is very difficult, so, or it's very hard to measure the change in entropy, but it's relatively easy to measure the change in tension, okay, over the temperatures, right, at constant L, right? So if we measure the change in tension, okay, about the temperatures, okay, then it's easily use these Maxwell relations, okay, that helps you to tell you that how the entropy changes, okay, over the length L, right, at constant temperatures, right? So that is the power of Maxwell relations, right? Okay, so basically you say that the experimentally, challenging to measure the change in entropy, to measure the change in entropy. Okay, but the Maxwell relations helps us to measure this, where the Maxwell relations, okay, helps us to, okay, so Maxwell relations helps us to measure this entropy change, us to measure this entropy change, okay, through the change in tension over the temperature, right, through the change in tension. Okay, so where the change in tensions which is possible to measure experimentally, right, so this change in tension, this is I think possible to measure experimentally, so which is possible, which is possible to measure experimentally, right, so it's clear why the Maxwell equations is important, right. Okay. So some point you cannot measure directly, or very difficult to measure the quantities, okay, but the Maxwell relations helps you that how it's related to other variables, and those variables are quite easy to measure experimentally, okay, and it's possible, right, and that is the one of the importance of the Maxwell relations, okay, the most important things, okay, so why the Maxwell relations are important, so this is one of the things that I discussed, okay, right. Okay, so any questions so far? So you can use these Maxwell equations, okay, you can calculate some, or you can also derive this kind of Maxwell equations for other systems, okay, like for the dielectric systems, for the magnetic systems, right, that is also, I mean, very crucial, so okay. Okay, so for example, let's say for paramagnetic systems, right, so for paramagnetic systems, so let's do one more examples for paramagnetic system, okay, so okay, so consider a magnetic moments, so consider magnetic moment arranged in a lattice, okay, at same temperatures T, okay, at some temperatures T side, so if you consider some lattice, okay, and at every point, so I think I have to draw properly, so it's been straight lines, so it's equal spacing, right, so assume that all the lattice spacings are equal, okay, and yeah, so every point, so this is basically these are the lattice points, okay, so let's, so these are the lattice points, okay, So consider magnetic moments arranged in a lattice, okay, at some temperature T. So magnetic moments, so consider magnetic moments, okay, arranged, okay, so arranged in a lattice, okay, at, let's say temperatures, okay, at temperature T, okay, and assuming that the magnetic moment cannot interact themselves, okay, so there is no self interactions, okay, so assuming magnetic moment cannot interact themselves, not interact themselves, okay, so this is the first law of thermodynamics. So then the first law of thermodynamics for these magnetic systems is basically your du is TdS plus BdM. Okay, B is the magnetic field and M is the magnetization, right? Okay, so here's the magnetic moment, and so M is the magnetic moment of the magnetizations. Here is the magnetic moment, and B is the field, magnetic field, right? So then you could first define the Helmholtz free energy F. So your Helmholtz free energy, so Helmholtz free energy F equals to U minus Ts minus Mb. So this Mb is the magnetic energy, right? So minus Mb is the magnetic energy, right? Or minus Bm. So this one is the magnetic energy. Magnetic energy, right? So then this df, the differentials is minus hdt minus mdb, right? So in using the same arguments, that df is a exact differentials, okay. So one of the Maxwell equation then becomes, so your del s over del b at constant temperature equals to delta m over delta t at constant b, okay, right? This is one of the Maxwell equations. Again, you see that the entropy, how entropy changes over the magnetic field B is del S del B is equals to delta M over delta T. So it's easy to measure experimentally the delta M, how the magnetic moments, the magnetization changes over the temperatures, okay. And that is related to how the entropy changes over the magnetic fields, okay, at a constant temperature, right? Okay. So see again the power of the Maxwell equations. Okay. Okay. So far any questions? So I'll stop here. So for today I'll stop here. Okay, and we meet the next Sunday at 4 p.m. Okay. I think there is also some extra classes the coming Saturday. Okay. So at 4 p.m. So we meet then at coming Saturday at 4 p.m. and also Sunday at 4 p.m. Yeah, any questions? So any questions, doubt you can ask. So you understand that what is the importance of the Maxwell equations, right? So that is very crucial. So that's why we discuss this, okay, at the end of today. So yeah, it seems that there is no more questions, okay. let's check that the chat box. Okay, no question. Okay, so it seems that there is no more questions, so then I'll stop the sessions. Okay, here, and see you tomorrow. See you on the next. Okay, so see you on the coming Saturday. Okay, at 4 p.m. and also Sunday at 4 p.m. So, okay, tata, bye bye.